Hi, my name is Uchanachima, and today I'll be solving Leetcode problem 141, linked list cycle. So for this problem, we're given the head of a linked list, and we want to determine if the linked list has a cycle in it. It says here there's a cycle in a linked list if there is some node in the list that can be reached, again by continuously following the next pointer. Internally, pos, or position, is used to denote the index of the node that the tail's next pointer is connected to. And we have to keep track that pos is not passed as a parameter, and we want to return true if there is a cycle in the linked list, otherwise we return false. So in the first example here, they give us a list that has 4 elements or 4 nodes, 3, 2, 0, and -4, and as you can see here, there's a cycle in this linked list because from the last element, -4, by following its next pointer, we're always going to be stuck in this linked list. As you can see, we never terminate after the tail. And it says here, pos is 1, because it says here, internally, pos is used to denote the index of nodes that tail's pointer is connected to. So as you can see here, the tail's pointer is connected to 1, so there's a cycle, because if there's not a cycle, tail's pointer should be connected to none, or in this case, -1. That's how they denote it in this example here. So in these two examples, there are cycles, because as you can see, the tail's pointer is connected to another node in our linked list. So I guess that explains it, and let's talk about how we can solve this. So there are 2 primary ways to solve this. The first way, I'll explain, is by using a nifty method which utilizes extra space. So what we can do is we can iterate through our linked list and store the memory location of each node, because we know that whenever we create some elements in programming, that element is stored in memory. So if we can store each node, or if we store each location of each node in a data structure such as a set, as we iterate through our linked list, we know for a fact that if we come across a node that we've seen before in our location set, or in our data structure, then we know that there's a linked list cycle, or that there's a cycle in our linked list. So let's go ahead and solve it that way first, and then I'll talk about how I can optimize it to solve it to use less space. So let's start coding the solution. So as I said, we can have a set to keep track of all the memory locations of each element in our linked list, a pointer to iterate through our linked list. So while a pointer hasn't hit the null element at the end of our linked list, we just do a few simple checks. So if the ID of the pointer node set, so basically if we have a memory location that we've seen before in our node set, we want to return true. Else we want to store this memory location in our node set. Enter. Store memory location in our node set, and then we also want to increment our pointer. And once we exit out of our linked list, if we exit out of the linked list, we know that we haven't hit a cycle. Let's run this code, see how it works. So this works, and this passes all test cases. Let's submit it. And this works, and it has pretty good time complexity. But as I explained before, so the time complexity of this code is going to be O of n, and as I explained before, this uses extra space, also O of n, because in worst case you might be storing every node in our linked list into our node set here. So to optimize this, why don't we use a little bit of a nifty method here. So this is called the tortoise and hare algorithm, or I like to call it the rabbit and turtle algorithm, because we know that a rabbit is faster than a turtle, right? So why don't we imagine that we put a rabbit and a turtle on a track, and if at any point in time our rabbit laps our turtle, or if at any point in time our rabbit passes our turtle, that means that we know there's a cycle in the linked list. Now this might seem a little bit ambiguous, my explanation, but think of it this way. If we have two pointers in our linked list, and we have one that moves twice as fast as the other one, we know that at some point, if there is a cycle, the one that's moving twice as fast will eventually meet the slower one at some point. So that's the idea here. So let's go ahead and code that solution. And as I said, this would decrease our space complexity from O of n to O of 1, because now we're only going to be using pointers, and we'll be able to remove this node set from our solution. So we call this fast, call this slow, and our while loop changes a little bit here. So I'm going to check while fast dot next, while fast and fast dot next not equal to none. So this basically checks if we're able to actually move our fast pointer, and if we are able to move our fast pointer, then we can go ahead and move it. So say fast equals fast dot next dot next, and the reason that I'm doing this is because we're moving our fast pointer twice to see if it eventually laps our slow pointer, and if it does, so if at any point in time our fast equals our slow, you just return true. But if that is not the case, then we have to move our slow pointer. Slow equals slow dot next, and as you can see in the solution here, we got rid of our extra data structure, thus decreasing our time complexity, or rather our space complexity, from O of n to O of 1. Let's run this code and see how it works. So this passes all the test cases. If I submit it, this works perfectly fine. And that is it for the video. Like, subscribe, and yeah, have a good one.